All right, so today I want to start on the second topic, which is infinite series. And so, can everybody see here okay? Or is this thing in the way? All right, so the idea here, and the infinite series stuff I'm going to talk about is coming from Matthews and Walker. So what we're going to be doing here really with infinite series today is really just going over the basics of it. And when we get into Fourier series, you'll see like another use of this. And also last week we hinted a little bit about how you could use infinite series when we were talking about as a possible solution to differential equations and using the power series. So the basic idea here is that we're going to be looking at the series and looking at convergence of the series as another way of writing an analytic function, but in a way that is simpler to understand in some ways, even though it's really tedious. So the idea is you have this concept of convergence, where if you take the limit as n goes to infinity for, say, the sum from little n equals 1 to big N, that is going to be Sn, or S infinity. And so basically S here is whatever the series converges to. So if S is finite, then this thing converges. And so there's two things you need to note. One is whether or not the series is going to converge, and if it does converge, what does it converge to? Because some of these series that you're going to run into just don't converge to anything. And so the idea then is if you have the sum, if n equals 1 to infinity, of a sub n, that's like having a1 plus a2 plus a3, etc., all the way up to the infinite term to get this sum. And so what happens is you can have, for example, 1 minus a half plus 1/3 minus 1/4, etc., and it eventually sums up to the natural log of 2, and so we say that converges. Because, you know, you can actually express natural log of 2 as the sum of the series. But if you take out the minus signs and make them all positive, then even though the numbers are getting smaller, this, when you sum it all up, is going to be equal to infinity, and so that diverges. So I'm not going to go into convergence tests. That's one of these things that, because there's so many of them, and and it kind of depends on what you're going to be doing for that problem. But in Matthews and Walker specifically, they talk a lot about convergence. And so what I want to focus on instead is different types of series. And then when you can recognize the type of the series, you can use that to recognize what this thing's going to converge to. So if it converges. So the first thing you need to know is this term of geometric series. And the idea. Yes. So the basic idea of the geometric series is that you have a term which is increasing with power with every step. So for example, a geometric series is something you can express as the sum from n equals 1 to big N of a constant times r to the n minus 1. And this is actually equal to a plus a times r plus a times r squared plus a times r cubed, etc. And you go all the way up to a times r to the n minus 1 eventually. And what happens is if you sum up this entire series, this is a plus by the way, you sum up the entire series, then this is going to become a times 1 minus r to the n over 1 minus r. Now, does this series converge or diverge? It depends. Yeah. Yeah. What happens is if you have the magnitude of r is less than 1, then it's going to converge. That was a trick question. And the reason why is because if you have a number less than 1 and you take it to the nth power, you're going to get, it's eventually going to, as n goes to infinity, it's going to be like a tiny, tiny number is going to disappear. So if you take 1/2 to the infinite power, it's going to be 0, effectively. If you take 1 to the infinite power, it's still going to be 1, in which case the numerator disappears and you have 0. If you take a number like 2 to the infinite power, it's going to blow up, in which case it's going to diverge and you're going to have infinity. So if you have r, magnitude of r is less than 1, then your series, your geometric series is going to become converge to a over 1 minus r. And then actually if you have the magnitude of r is greater than or equal to 1, okay, now what happens is in the numerator, if it's equal to 1, you're going to get 0 over 0, which could be infinite, so we'll call that divergent. If it's 2, then you're getting an infinity, so we're just going to say that this diverges. And so this was the limit as n goes to infinity of sum of a r to the n minus 1. And also another way to write this is basically the limit as n goes to infinity for a times 1 minus r to the n over 1 minus r. Okay, so this is probably going to be the absolute most useful series you're going to run into, at least this week and probably for the rest of the semester. And the reason why is because it's just so simple and it's so easy to pick out. And so if you see something and it happens to follow this pattern, and by the way, infinite series is all about pattern recognition. If it follows this pattern, then it's a geometric series. If it's a geometric series, you know what it converges to. So as long as you can write it as like something like that, you're good. So for example, if I had a series and it looked like 1 plus sine of theta plus sine squared theta plus sine cubed theta. Okay? This could be a geometric series where a is equal to 1 and sine of theta is equal to r. So if you take the convergence of this, because sine theta is, let's say we're limiting this so that sine theta is less than 1. then this could actually converge to 1 over 1 minus sine theta. So there's a way to do that. What? It would converge to that, yeah. If you expand this thing out to infinite number of terms, then it converges to that. And so this is how you would use this, because you're saying because you're just recognizing that this series happens to be a geometric series, and now you know what a geometric series converges to, so therefore you know your answer. So just making your life simple in the long run. If you can make it look like a geometric series, that's one way to solve the infinite series problem. What you're going to see on your homework on this is basically going to be some of these are going to be series that you're going to see, and you're going to have to figure out what it converges to. And putting it into your calculator and just adding up the numbers isn't the way we do it. You have to actually figure it out. All right, the next series is called a harmonic series. And the idea of the harmonic series is that this is going to be something that's going to diverge. But what we want to do is we want to know or be able to understand the series and at least kind of put bounds on it so we have a rough idea of what it's going to become before it diverges. So what happens is the nth term is going to go to 0, but before you get there, you're going to have like 1 plus a half plus a third plus 1/4, etc. And the last term is 1 over n equals s to the n. If you take this to infinity, of course, it disappears. So the way we can understand the series is we group the terms. So let me write out a few of the terms. And then I'll just go all the way to 1/16, okay? So what we can do is, if I put these two terms together, I put these 4 terms together, and I put these 8 terms together, then what happens is each one of these terms in the parentheses, or each one of these brackets and parentheses, looks like 1 over p plus 1 plus 1 over p plus 2, all the way up to 1 over p plus p, where p is the number of terms in the parentheses. So for the first one, p is equal to 2, so we have 1/3 plus 1/4. For the next one, p is equal to 4, so we have 1/5, 1/6, 1/7, and 1/8, and so on. And so this can be written up as a series where you're basically summing from n equals 1 to p of 1 over p plus n. So in other words, it's a series inside a series. Now, with each one of these, you'll notice that if you look at the first term here, this is approximately 2 over 2p plus 2. I'm just multiplying the whole thing by 2. Because the last term is just equal to 1 over 2p. Okay? And so what that means is that when you sum up this series, it's going to have a value somewhere between 1/2. So if you take this series, it's going to have a value somewhere between 1/2, which is taking this last term and this multiplying it out, for each one. Or, on the other hand, it's going to have a number that's going to be less than 1. Because if you take P of these, it's going to be slightly less than 1. So each one of these brackets that you're adding is going to add somewhere between 1/2 and 1. So if I say, the sum S of n, and I want it for 3, that's an easy one, because I know that it's going to be some number that's going to be greater than 2, but it's going to be less than 3. Because you're going to have, it's going to be greater than 2 because you're going to have 1.5, and then you're going to add another 1/2, and then you're going to get this term. So you're going to end up having at least 1/2, but then you're going to have some number that's going to be less than if you take this and you add up 1 for that.
Why did you rewrite the first time at school?
Oh, the reason why is because I wanted to kind of put this on the same footing.
Absolute piece.
Right. And so you can see really easily if you put this as multiply that by P, you get 1. I guess you didn't really have to multiply it, but you could just makes it a little clearer for me. So for example, S1 is equal to 1. You can see that there. S2 is equal to 3/2. S3 is equal to the 1.5, and then you're adding no more than 1/2 because of these two. So you could say that whatever comes out of that is going to be P is equal to 2, so you just add in that. So let's say that's going to be greater than 2, which makes sense because if you add, let's see. Well, it's going to be in the neighborhood of 2. And then S4, you're going to have all of these. So now you have the third plus a quarter plus the 2, or the 1/2, and the 1. And so you can see that you start to develop a range here where you know that this is going to be more than 3/2, but it's going to be less than or more than 1.5 plus 1/2, but it's going to be less than if you add 1 to it. So you get a range there of between 2 and 2.5, and then the next one adds another factor of that. So when you add this next bracket, this next group here, what happens is you're going to get another group, which is going to be, we'll call it S4, and that's going to be adding maybe another 1/2 at least, but less than 1. So you know that this is going to be something greater than 5/2 when you add that whole thing on there, but it's going to be less than 3. Does that make sense? I think I confused you guys a little bit.
I get it. I mean, I understand.
Yeah.
How you're getting those numbers, but I don't understand.
Because I think,
like where it's going. Like, what's the point of understanding that? Do we get it?
oh, because you want to know just roughly, let's say we have 100 terms, rather than have to actually physically add up 100 terms, because we're lazy, you want to be able to say S equals 100 is going to be in this range. And you can kind of get that quick and dirty number without actually having to add everything up.
So you're making an assumption that behavior on a given interval defines behavior in the inference game?
Right. Right. So what happens is you could say that this number right here is somewhere between 1/2 and 1, okay, for this group. This group right here is going to be somewhere between 1/2 and 1. This group right here is going to be somewhere between 1/2 and 1. And so the whole idea here is just to kind of illustrate how you can, even though the whole thing is going to diverge eventually, you can treat your infinite series as a sum of infinite series, which can come in handy in some situations.
Can't you have, essentially a signal aliasing where the bracket set is diverging or converging for the entire series that you're doing that?
You could, where maybe the bracket set are canceling each other out in the long run. And in which case you have to look at, but the whole point of this was that each one of these brackets is going to be the same. So they should be adding together. Now you could create some weird series where it alternates signs between each bracket set, and then you get something really different. And in which case then you're subtracting infinite series and from each other, and it's, that's a whole different ballgame. Yeah. What's going to happen with this is that when you do the problems, some of the stuff will become more clear when we do the recitation on this stuff on Thursday. You'll get a chance to see a little bit more about how to approach different things you can do with this infinite series. Because I'm really just starting at the beginning and just kind of scratching the surface on it. Okay. All right, the next thing I want to talk about, these are called the familiar series. And these are basically the series that sort of they're going to show up, and you can kind of open up a book on formulas and tables like Shalom's outlines, and you'll just see all these series in there, and then it'll be up to you to kind of recognize them and use them in different ways. For example, 1 plus x to the n. Okay, this can be expanded out as 1 plus nx plus n times n minus 1 x squared over 2 factorial plus some other stuff. And you can also write this out as the sum from, I don't want to use n, alpha equals 0 to infinity of n factorial over n minus alpha factorial times x to the alpha over alpha factorial. So what's happening here is you're summing up all of these different terms, and eventually these terms, when you sum them all up, you get this nice analytic function. Another one, and then this is the well-known series. You can see it's not a geometric series, obviously. Another one is the exponential term. And the exponential term looks like 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. And you just follow the pattern. And this one sums to the sum alpha equals 0 to infinity x to the alpha over alpha factorial. And then the sine of x, which is just x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, etc. And so this, if you look at cosine, by comparison, it's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc. Now here's the neat thing. When you put these two together and look at these two side by side, it becomes very clear that if you take cosine plus I sine, then the result is going to look just like the exponential term. So this is that where you get this whole e to the ix is equal to the cosine plus I sine. And you can see that the sine term is the odd part of the sum, where you can actually, it's like every other term is going to be sine, and the cosine is going to be the even part, where that's every other part. And you can see that if you take the x, for example, you switch the sign on it, then cosine is going to be symmetric because it doesn't change because these are all squared or some even power. The sine is going to change signs because it's all odd powers. And the exponential term is just adding all those together. So you can see that all of the mathematical properties that the analytic function obeys, the infinite series is going to obey, and vice versa. So if we take a derivative of the infinite series, we're taking a derivative of the analytic function and vice versa. That's the whole reason why we're going to use infinite series, because you can literally, if you want to take the integral of this thing, it's really straightforward because it's just simply taking the integral of the series, where you just know the integral of x, you know the integral of x squared, etc. And the same thing with all the derivatives. And so you could prove from this series, for example, that taking the derivative of sine is going to give you cosine, right? And everybody can see that? Okay. Another one is natural log of 1 plus x. That comes from taking the derivative of this first term I have up here, but setting n equal to minus 1. So if you set n equal to minus 1, then the derivative of that is going to give you the integral of that is going to give you the natural log, and that is going to be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, etc. So the integral of 1 plus x to the minus 1 dx. Or the inverse tangent of x is equal to x minus x cubed over 3 plus x to the 5th over 5 minus, etc. And that's the integral of 1 plus x squared. What?
Is that a 1 or a 4 on the at the end of the limit?
Oh, here?
No, at the very end of the series.
Oh, here? That's a 1. Sorry. How's that? Okay. All right. So if you have 1 plus x squared, it's the minus 1, and you take the integral of that, then that should give you the tangent of x. And you can get this series by just simply taking this familiar series up here and squaring all the x terms and setting n equal to minus 1. So the idea is that you can use the familiar series in order to generate other series or to understand what it is you're working with. And if you think about it, these, I wouldn't even count the last two because you can get those easily from the integrals, but these 4 you can use as the basis for most functions you're going to run into. If you've got an exponential, you got sine, cosine, you got some combination of 1 plus x to a power.
So for the homework, if it's in Shelms or we think it's down to something that's in Shelms, then we're done.
Yeah, but it won't be in Shelms. I mean, what I might give you is you might see a series, and you have to tell me what it converges to. And the trick to that is that sometimes x is going to be equal to 1. Okay? Or x is going to be equal to a number. In which case, you have to kind of think about it. Think about, well, what if I take this number and I replace it with x, and then I can turn it into a series, and then I can see it looks like this familiar series, and now I know what it converges to. For example, if I say x is equal to 1 here, then this series right here is going to look a lot different. And I could have the natural log of 2 is going to be equal to 1 minus 1/2 plus 1/3 minus 1/4, etc. Right? Now you can see that, but what if I went the opposite way? What if I gave you this series and asked you what it converges to?
Well, it's still not quite right? Because it's not 1/3 and 1/4, it's 8/3 and
No.
1 plus x.
Yeah. X is equal to 1. Yeah. Okay, so anyway, so the idea here is that you can kind of work backwards from that. So if you saw this series, you could kind of figure out from this series that it's going to converge to natural log of 2, and you know that because you can compare it to this equation and kind of pick up the pattern. And one way to find the pattern is to look at what's going on in the denominator, because you could see, for example, in the exponential term, the sines and the cosines, they all have these factorial terms. But these terms involving the natural log or the inverse tangent, these are not. So you might be able to pick up a pattern there. And I'll get into derivatives and integrals, but basically you can take derivatives or integrals of the infinite series in order to turn it into something that you might be able to recognize. And that's another way to do it. Or you can kind of combine all these. So it kind of requires a certain creativity to be able to look at this and sort of figure out what the pattern is and figure out what's going on inside of it, and then to kind of stick in the numbers that make it work. So, for example, you can, I did it here with natural log of 2, and I also showed you how you can basically describe these two familiar series integrals of the other familiar series. So you can kind of get a feel for what's going on there. Okay. But if you got a series like this, then I guess it's kind of save it for recitation, like kind of going into how you can manipulate these things in order to see what the pattern is. You also do run into this problem where you might have a series or try to generate a series out of these familiar series, and you have these exponential terms in the denominator, and it doesn't quite make sense, and that's where Bernoulli numbers come in. And so the idea of the Bernoulli number is you have something like x over e to the x minus 1. Now, this is not a familiar series, obviously. It actually looks like a combination of the exponential familiar series and something involving 1 plus x to some power, right? So we can kind of think of this as a power series and just assume that anything can be written out as a power series. Because if you look at these familiar series, every single one of these is a power series. It's just a matter of figuring out what the coefficients should be in order to make it work. And if you got the right coefficients, then you're done. So what we can do is we can take the exponential term, which is e to the x minus 1, and it's basically this series here, but getting rid of the 1. And we can multiply this term in the denominator across. And so what we end up with is x is equal to this power series, which we're kind of guessing at, multiplied by e to the x minus 1, which is equal to x plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Right? And so what happens is that these terms have the factorial terms in them, these other terms don't. We can now simplify this even more, divide through by the x, and we have 1 is equal to c0 plus c1x plus c2 x squared plus etc. And then you have 1 plus x over 2 factorial plus x squared over 3 factorial, etc. And now you can just multiply this out term by term, and then you can equate the like powers of x. The only problem that you run into is if you want to do the comparison, you have to have these factorial terms in it, or at least that'll make things a lot easier, right? So this is where the Bernoulli numbers come in. We're going to set each of the coefficients we guessed equal to some new Bernoulli number divided by n factorial. And by doing that, we're basically implying that our series is going to be equal to a power series involving the factorial terms. So it just takes a little bit different form. And so now, when you put in the Bernoulli numbers, you can have this as 1 equals b0 plus b1 over 1 factorial x plus b2 over 2 factorial x squared, etc. And then you have 1 plus x over 2x. 2 factorial plus x squared over 3 factorial plus some other stuff. Okay, now what happens is you equate the powers of x as you multiply this out. And you can see, for example, on the left-hand side you have 1, and then you get b0 times 1 is the only way to get something with no powers of x, so that's b0. Then you have, for the next term, you're going to have 0 for x, the x term, and that's going to be the same as here. You have b0 times x over 2 factorial, so it's b0 over 2 factorial, and then you have b1 times that term, so plus b1 over 1 factorial. And then you have 0, and you do the x squared term, which involves this term, a combination of these two terms, and that term. So we have b0 over 3 factorial, by multiplying it over here. We have b1 over 2 factorial and 1 factorial, because you have it this term times this term. And then you have b2 over 1 factorial, 2 factorial, because it's multiplied by that first term. And then you just keep going with this. And then what you'll find after you figure out enough terms is that, well, of course, b0 is equal to 1. B1, once you know what B0 is, you can figure out what B1 is. And that's equal to minus a half. B2 is equal to 1/6. B3, B5, and B7 are all equal to 0. Because what happens is you'll see that all odd numbers are going to just kind of fall out. And so you can use that to figure out the entire series. And once you have a series, then you effectively expanded out that weird function into an infinite series. Yeah?
So one integration of one and the other was zero.
Oh, well, I think it's because you're ending up with some constants, and so basically this is going to look like, if you expand this out, it's going to basically look like a couple constants, and then you start summing the series. So it's not unusual that that we might have one odd term which is non-zero, and then all the other odd terms are 0, and then you just, when you express it as a summation, you have these constant terms plus the summation over all even values to give you that result.
So is it usually all first term has to equal to some value, or you can just select
It's usually going to be the first term or something like this. Yes?
Is it because B0 is the only number multiplying by just the 1, the only one that has to be 1 out of all those?
Mm-hmm.
Okay.
And then B1 is in a similar situation because B1 here can also be multiplied by 1, but it's going to have to cancel out another term involving B0.
So I mean, like
So-
when I'm without the X term in front.
Oh, yeah. I thought you were asking about why B1 is also non-zero. Okay, so these are Bernoulli numbers, and so what happens is we can use this new series now. And let's suppose we have the cotangent of x is equal to I e to the I x minus or plus e to the minus ix divided by e to the I x minus e to the minus ix. Okay, so in this case, ix is equal to y over 2. We're just using this as a substitution because I don't like all these i's floating around.
So the second one solved with using the minus by x when we make it 1?
Yeah, sorry. The precision of these things is never as great as you'd want them to be, but yeah. Mm-hmm. Yeah, because it's basically that. It's just basically cosine over sine. Right, but there's a cotangent. Yeah. Well, I can. Okay. Yeah. Anyway, so we're going to write this. We're going to substitute the variable just to make this a little easier. And so we can say cotangent, that helps, of x is equal to I times e to the y over 2 plus e to the minus y over 2 divided by e to the y over 2 minus e to the minus y over 2. And so once you have this, the reason why we use y over 2 instead of y is because we can multiply the top and bottom by e to the y over 2, and you get I times e to the y plus 1 over e to the y minus 1. And so now you have that, you can actually take the numerator and you can split it between the two, and you can get, well, actually we can add a term and subtract a term. So we're going to actually add e to the y. We're going to add in e to the y, and we're going to subtract an e to the y. Okay? When we do that, the minus e to the y and the 1 are going to basically give you a minus 1 term. And then the e to the y plus the other e to the y is going to give you a factor of 2. So you can take this and you could turn it into I times 1 plus 2 over e to the y minus 1.
Can we just add and subtract the 1 there? So that e to the y
Oh, yeah, we could do that. Okay, forget about what I just said. Minus 1 plus 1. Okay, and so yeah, you could do that, and you got something. Oh, we just we just added and subtracted a 1. So you have e to the y minus 1, and then you take e to the y so this is actually equal to e to the y minus 1 plus 2 over e to the y minus 1. Okay. So now we have this. We split it up into 2 parts. And the reason why we did that was because now if we take this whole thing and we're going to pull out a y over 2 from it. So we're going to rewrite this as 2I over y times y over 2 plus y over e to the y minus 1. Okay? Now what we have here looks a lot like this series, right? So we can take this second term, this really complicated looking term, and it is essentially our infinite series that we just figured out. And we're adding to that a y over 2 term, and the y over 2 term is basically, it's basically this first term in the infinite series, the constant term, right? Or sorry, the second term here, because we have here a factor of minus a half, and if you take the minus a half in B1 and you have into the 1, right, then that's a minus 1/2 x. So this series that we created is really going to be minus 1/2 x plus the sum over all the even terms of the Bernoulli numbers x begin. And so by having this factor of y over 2, we're getting rid of this first term. And so now this is going to be 2I over y times the sum over all the even terms of bn y to the n over n factorial. So now we've basically turned our cotangent into an infinite series. Okay? So we want to get back to x because this is all written in terms of x. So we're going to replace y with 2ix, and so the cotangent of x should be equal to 1 over x times the sum over the even terms of minus 1 to the n over 2 b sub n 2x to the n over n factorial. This is just substituting numbers back. And you'll notice here that even though y is complex, you end up having y to the n, and so y to the nth power ends up giving you all of the i's basically turning into negative 1s. And so it's either negative 1 or negative 1 squared, which is 1. And so that's why we get the sign flipping here. Also, another thing you'll notice is cotangent is real. It's not complex. But we had a complex stuff in between, and when we did our infinite series, it turned out to be real, which is what we expect because, you know, the infinite series expansion is the function. It should behave exactly like the function. All right, any questions so far on this? Clear as ice? Kind of foggy ice, something like that. Okay. By the way, this is not an extremely long lecture today, if you're wondering, because this is one of those where, you know, this is one of those where you guys will be out of here by like 5:30, 6 o'clock, as opposed to, you know, getting out of here at 7. So all I can say is enjoy it now, because later on in the semester when we hit some other heavy stuff and you're out here, you know, we're barely getting out of here by 7 o'clock. It used to be 10 when it started at 7. Then you'll be thankful for this. So.
Was that derived from something else that was complex?
No, cotangent of x. Cotangent of x is basically just flipping the sign, the tangent over. So it's just basically equal to 1 over tangent of x. It's just a funny way to say it. You know. Yeah. Think it.
I was trying to see what that expression came from. You have all these different.
Because this is like cosine over sine, right? And remember, cosine is e to the ix plus e to the minus ix over 2, and sine is e to the ix minus e to the minus ix over 2i. So the 2 falls out. Yeah. It's like you almost have to go back and look at trig again. It's been a while. And that's part of the purpose of this course, and part of the way I structured this is because I'm expecting that some of the math we're using here, especially in the first half of the class, is stuff that you've seen before. It's just probably been a while since you've seen it, so it takes a little bit of warm-up. And so everything in the first half of the course is something I expect that you've had some exposure to. It's only in the second half that we're getting into stuff that, you know, is going to be kind of new. And it's going to feel a little bit new and different for most people.
Can I ask a sort of off-topic question regarding
Sure.
prediction? Just because I had a student ask me today why, for like an inverse tangent, you write tan and then like a -1x, where like for a cosine, that could be square root of cosine. So
Right.
say cos the 2 and then x,
Right.
you're squaring the whole thing. But like an inverse tangent is not that.
Right.
You take an inverse
Because,
or like an
well, think about it like this. This is like tangent of x to the -1,
Right.
as opposed to tangent inverse 1x. So you gotta keep in mind these two are not the same.
Right, but for positive exponents, we bring it inside. You know what I'm saying?
Right, right. I know what you're saying. Like it's weird because because remember this is an operator and not a function. Yeah, it's a function and not like a. So it's its own thing.
It's almost like output something, right?
Right.
Yeah.
I just had a student asking that today.
Yeah, yeah. But yeah, I mean, I guess when they're first seeing it, it just looks weird why you would write it like that. Yeah. So I mean, you can use the arc and you can slip a little C on here, and it kind of clears it up a little bit. But I think this is one of these things where it's a notation-heavy thing where you can't really. It depends on how people want to define it. Yeah. Actually, you know, it's like you hear the joke. You've got. I've seen students do this when I was teaching like algebra-based physics. And they have something like tangent of x is equal to 1. Find x. And so, of course, they say x is equal to 1 over 10. But, I don't know, spend some time teaching college physics and you'll see that a lot. And so you just have to tell them, no. But I saw that a lot, and that's kind of why I don't teach introductory physics anymore. So, next thing I want to talk about, transformation of a series. I mean, luckily I haven't had to teach pre-med in like 15 years, and so it's been a lot nicer since then. My wife is a pre-med, I can say that, but they're the worst. Anybody who thinks you can memorize your way through a physics class, and a lot of pre-meds think they can do that.
You memorize every formula you improvise one thing. They memorize, well, I used to be today, you memorize everything in
Right. That's kind of how they're taught, but I could tell you, I can memorize nothing. I have to write my own name down in my analysis. I don't. So I'm not memorizing a single thing. Everything I know, I'm just. The process is just re-deriving it on the spot, so it's like a totally different thought process there. So anyway, the example here when I talk about transformation of a series is, let's suppose you have a series, f of x is equal to 1 plus 2x plus 3x squared plus 4x cubed, etc. Okay? Now, this is, at first glance, if you're trying to figure out what this series is, it takes a little bit of creativity and it takes a little bit of vision to it, because what's happening here is not a geometric series, because the coefficient keeps changing. And it's also not a familiar series either, right? But if you have a little vision with this, if you integrate the series, which you can easily do, then you could see that this is x plus x squared plus x cubed plus x to the fourth, etc., which is a geometric series. And the geometric series is like a is equal to 1 and x is equal to r. And so the result of that is going to be x over 1 minus x, because it's really x times the geometric series, right? And that's what it converges to. Now, if you want to find the original series, you just simply take the derivative of your analytic solution, and that's going to be equal to 1 over 1 minus x squared. And that is your f of x. So in other words, we found the infinite series by just simply taking what we got, integrating it until we got something we recognized, and then taking a derivative till we got back to where we started. And you could do it the other way too. you could have taken a derivative of this series, and hopefully that would have gotten you to something you recognize, but it would have been kind of hard to see with this. Yeah. Or, let's see, the other option is if you could have recognized it from the familiar series, which is a little bit harder work because it's not quite clear. Okay. All right. And you're going to see a lot more examples kind of like this. What the trick is going to be, and I'll throw this out as some of the problems, is what if they're presupposing x is equal to 2 or x is equal to 1, then you have to kind of put back x could be anything. So in other words, let's suppose we had the same series, but it was just a series of numbers. And we had, let's say f of 1/2, x is equal to 1/2. Then that would have been like 1 plus 1 plus 3/4 plus 4/8 plus, or something like that. It would have been something weird like that. Then this thing still holds. It's just a matter of you'd have to kind of see this pattern and figure out, well, if I pull out the half, and I assume that these are going by a half, then it works. Or something like that. Most likely, it'll be something like f of 1, and you'll have a series like 1 plus 2 plus 3 plus 4. And what happens is, in order to understand what's going on, you'd actually have to say, there's an x in here that we don't see. I'll get into that in when we do the recitation, because it'll naturally kind of fall out of some of the problems you guys are going to be looking at. Another example is f of theta. F of theta is equal to 1 plus a cosine theta plus a squared cosine 2 theta, etc. Okay? Now, this is one where it's a little bit weird because you have this cosine 2 theta, so it's not quite a power series. But what you can do is you can think of this as a power series by thinking about it as the real part of an exponential. Like this. And you can see that these are equivalent to each other, right? The only difference is this looks like a geometric series. The first one doesn't. And so you can write out the geometric series as being the real part of this, where your r, oh sorry, this is a squared. Your r is going to be equal to a e to the I theta. So you're going to sum over 1 minus a e to the I theta. And then this, now when you take the real part, what you have to do is rationalize the denominator. So you multiply top and bottom here by 1 plus a e to the I theta, or minus I theta. Actually, sorry, I guess this would be a minus here. Because we just multiply it by its complex conjugate, so this needs to be a minus sign, not a plus sign. Oh, I'm just talking about to rationalize the denominator. So this way, when you multiply it out, you've got 1 times 1 The middle terms are going to cancel out because you have an opposite sign. And then, oh, sorry. Yeah, they are. They are. Because, well, they're going to add together to give you a cosine. So this is going to be like the real part of 1 minus a e to the minus I theta divided by 1, and then you have a e to the minus I theta, a e to the plus I theta. You add them together and you end up with a minus 2 a cosine theta, right? And then the last two terms, they cancel out and you end up getting the plus a squared. So the determinant of the denominator is now rational, it's real. And in the numerator, you're just trying to find the real part of that, and so you end up with 1 minus a cosine theta over 1 minus 2a cosine theta plus a squared. Okay. Not the smoothest, but that works. And so by doing that, you can effectively take your infinite series, as weird as it looks, or take this thing and turn it into an infinite series. And so there's basically two things you do. You either solve for the infinite series, where you're given a series and you have to figure out what it converges to, or you have to take an expression and turn it into an infinite series. And so mostly what we've been doing here so far is just solving for the infinite series. And, you know, given an infinite series, what's it converge to? You're going to have some problems that are going to do both. But, and that's because realistically, when you're actually working out these problems on your homework, you're going to actually, when you're actually using this later on, you're mostly going to be converting stuff into infinite series, but every once in a while you will have something like that you have to convert to an analytic solution. And then this is useful because when you're trying to take a derivative or an integral, sometimes expressing it as an infinite series just makes it a heck of a lot easier than going the other way. You just brute force going at it. All right, the last thing I'm going to go over today is the most important infinite series you're going to see, which is the Taylor's expansion, which you guys should all be familiar with. And so the way this works is basically you have some function f of x, and you're assuming that it's basically well-behaved. It's got a continuous nth derivative, and it's going to be in some range between a and b, okay? So the Taylor expansion is not meant to hold everywhere universally. It's meant to apply when you're fairly close to a certain point. And so what happens is you're going to essentially use the fact that when you integrate the nth derivative of the function, then what comes out of that is going to be the n minus 1 derivative and then you're going to evaluate it between a and x, or whatever your limits are. And so what you're going to get is going to be the n minus 1 derivative at x minus the n minus 1 derivative at a. Okay. So this is going to be, a constant, effectively, because it's at a constant point. And this term right here is going to be a dynamic variable. It's going to depend on x. So now we do the integral from a to x of the second derivative, or two integrals. So now we do integrating from a to x2 and then from a to x. Of the nth derivative term. Okay, and when you do this, of course, now you're integrating the second derivative of what you got before. And so what happens is, this last term, of course, is still a constant, but this term is dynamic, so when you integrate that one, you get the n minus 2 derivative of at x minus the n minus 2 derivative at a, and then this last term, since it's constant, it's just being evaluated at the difference between a and x. So it's going to be like minus x minus a at the n minus 1 derivative evaluated at a. Okay? And so what you have to do is, if you can imagine, you just do this many, many, many more times. And eventually you're going to have the evaluation from a to x of the nth integral. And so where originally you're integrating from a to x2 of this nth derivative term. And so when you do this enough times, eventually you're going to end up with this f of x is going to pop out, because you've just integrated it so many times that you're back to the function. And then you have the value of f at a, which is something you can measure, you supposedly know. And then there's going to be a bunch more terms which are going to look like this term here, where it's going to be like x minus a over n minus 1 factorial, and this is going to be the n minus 1 power of the n minus 1 derivative evaluated at a. And so what you do after you've done all this, and now that you have f of x, is you flip everything around. So now you have f of x is equal to your f of a, and then everything else looks like a perturbation on that. So we have plus x minus a of f prime of a plus x minus a squared over 2 factorial f double prime of a plus some other stuff. And then eventually some of that other stuff is going to eventually get to a x minus a to the n minus 1 power over x minus 1 factorial of the n minus 1 derivative of a plus the remainder of this. And the remainder, the r sub n here, is really going to be equal to all these integrals that are left over where you're doing the nth integral or the infinite integral or whatever of this. And so the way that you get rid of this is using the mean value theorem, which basically says that if you integrate some function, let's say g of x, from a to x, then the result of that is going to be equal to x minus a times g at some value, where this value, zeta, is somewhere between a and x. So in other words, if you want to, this works with 1D or multiple dimensions, is that finding an average is just as good as finding an integral. And so, like I've run into this in computation work where I have a quantity that I need to integrate in order to find out what's going on with it. Instead of calculating the integral, what you could do is if you find the average over all values, then you know that if you multiply that average times the volume of your system, then you get the total, the total sum or whatever, the total integral. And so this is the same thing here. And so because of that, you could say, well, r sub n is really just equal to x minus a to the n over n factorial times the nth derivative of the mean value. Because once you have this mean value of this, then it's just a matter of just multiplying it by the x minus a, and then you're doing it n times, so that's why you get these factors involved. And also when you look at this, this looks a lot like it fits into the pattern here. So therefore, we get what we know of as the Taylor expansion, which is f of x is equal to f of a plus x minus a times f prime of a plus x minus a over 2 factorial times, this is squared, times f double prime of a plus some other stuff. And usually this is about as far as you go, because usually you don't really get much higher than second derivatives in physics. And so you can also write that as a sum from n equals 0 to infinity of x minus a to the n over n factorial f to the n of a. And so this sort of gives you what you can take as your solution at a point by just simply expanding out as the derivatives around that point. And you can also take x and you could replace it with x plus h, where h is just some little difference, in which case you have f of x plus h, where you just shifted everything a little bit over, is equal to the sum from n equals 0 to infinity of h to the n over n factorial of f of n of x. Now, I'm not going to go into it here, but like in a numerical methods class, you learn that this is actually what you use to calculate derivatives. Like, the simplest way to calculate a derivative in numerical code is to actually take advantage of the Fourier the Taylor expansion in order to come up with what your derivative should look like. Where you're basically solving for this term as opposed to the f of x term. And then you can get a second derivative too, and so on. I'm just kind of using these Fourier, or these Taylor expansions. Yes?
Why is it the h to the n on top not h minus a?
Oh, because remember x is replaced by x plus h, and so when you put that in here, then you have x minus, let's see, I shifted everything over by h. So I use, right. Yeah, I know what you're talking about. Here's the name of it. Yeah. But anyway, if the difference between x and a should be h effectively, or when you're defining this.
Call x plus h, or call x minus a, x plus h.
Yeah.
Call x minus a, h.
Right.
Call x a plus h.
Yeah, I think that's probably a better way to put it. And therefore, a is equal to x minus h, which is effectively going to give you this, everything else here. All right, other questions?
You're recording the Thursday.
Yes. Yeah, that's online. Thursday's online, and all you have to do now, it should be converting it to MPEG-4. So it may be done by now, but if you want to download it that way, you can do it. Okay. All right. No other questions. It's a short class today. And just let me know if you have any questions on the homework. The first homework is going to be due next Tuesday, just a reminder. And this Thursday, we're going to be talking more about the infinite series and going over some more concrete examples.